Hello, I'm back with part 2 of our investigation of limits of sequences, and I've got a few more examples I want to work. Uh, First off, we're starting where we left off, looking at the sequence -1 to the n plus 1, 1 over n squared. If you look at the notes that I posted on Canvas about alternating sequences, then what we want to utilize is we want to look at the limit as n goes to infinity of essentially the absolute value of the terms that we're looking at. And so in this particular case, we want to look at the limit as n goes to infinity of 1 over n squared. And using what we know from what we saw back in chapter 2 in calculus 1, this is going to be the same as the limit as x goes to infinity of 1 over x squared. Excuse me. And we know that as x gets really big, x squared gets really big, and the reciprocal is going to get really, really small, and so that's limit is equal to 0. And so by our result on alternating sequences, we get to conclude that the limit as n goes to infinity of -1 to the n plus 1 of 1 over n squared equals 0 as well. The idea is that even though the terms are alternating in sign, because they're getting close to 0 on both sides, the limit of the sequence is going to be 0 because both the positive and the negative terms are heading towards 0. Whereas in the next example, notice this is the sequence that we came up with in one of our earlier examples from the first video, -1 to the n plus 1, n over n plus 1. We're going to look at the limit as n goes to infinity of the absolute value of this, or n over n plus 1, and we know that we're hoping that we can plug in x, and because the degrees of the numerator and the denominator are equal, this is something we could have done with our tangent example in the first video. We know that the limit is going to be the ratio of the leading coefficients, and so I'm going to get 1 over 1 over 1. But in particular, we notice that 1 is not 0. And so by our result about alternating sequences, then the limit as n goes to infinity of -1 to the n plus 1, n over n plus 1, does not exist. And the idea here is that the even terms are approaching -1, the odd number terms are approaching +1. If I were to try to draw something here, and this is going to be a very crude, rough diagram. Then I'm starting off, and I'm alternating signs, and as n gets bigger, my terms up here are approaching +1. My terms down here are approaching -1. So the terms overall are not approaching any one single number, so the limit does not exist. Our next two examples involve geometric sequences, and again, this is something I've referenced on the notes I've posted on Canvas. So once we note the ratio of a geometric sequence, then we just need to just see where that lives on the number line, and that tells us what our answer is. So we know that if we take a number between -1 and 1 and raise it to higher and higher powers, those numbers get closer and closer to 0. And so here we observe that the absolute value of -4/5 is less than 1. So the limit as n goes to infinity of -4/5 to the n is equal to 0. Whereas in our other example, the absolute value of 7/3 is bigger than 1. It's positive. So we would get to conclude that the limit as n goes to infinity of 7/3 to the n is positive infinity. If we'd had, say, an h sub n equals negative 7/3 to the n, here the absolute value is bigger than 1, and negative 7/3 is less than negative 1, we would conclude that the limit as n goes to infinity of that sequence does not exist. And again, it's that alternating sequence thing. This is a sequence that alternates between positive and negative numbers. In this case, the even number terms are going toward plus infinity, the odd number terms are going toward minus infinity. We would know that the limit doesn't exist, but we actually can't even say that it's either plus infinity or minus infinity because of the alternating signs. Then here I've got a nice sequence, and we're going to remind ourselves that L'Hopital's rule does come into play here. And the first thing I'm going to notice is that I could rewrite this as n squared over e to the n. And as n goes toward infinity, we've got an infinity over infinity indeterminate form. That means it's particularly ripe for an application of L'Hopital's rule. So remember, we're going to convert over to a continuous variable x. It doesn't make sense to talk about the derivative of a sequence because the graph of a sequence is a picture of discrete dots, and so there's no such thing as a tangent line. It's not a smooth connected curve. And so by L'Hopital's rule, that's going to be the limit as x goes to infinity of 2x over e to the x. That's still infinity over infinity. So we get to apply L'Hopital's rule one more time. And as x goes to infinity now, we see that the denominator is getting huge, and our limit is going to be equal to 0. So the limit as n goes to infinity of n squared e to the minus n equals 0 too. So don't forget L'Hopital's rule. My last example involves the terms increasing and bounded sequence. And so I've got a sequence here. I want to show that it's an increasing sequence, but also it's going to be bounded too. So I'm asking you to look up those definitions and report back on them in a discussion board on Canvas, but we can work with this. And so to show a sequence is increasing, one way we can do it is we can look at the difference between successive terms. Now, if the terms of the sequence are getting bigger as n gets bigger, then a sub n plus 1 should be bigger than a sub n. And so therefore we should expect that a sub n plus 1 minus a sub n is bigger than 0 for all n. So this is what we want to show. So we'll start there with the increasing part. So let's look at a sub n plus 1 minus a sub n plus 1 minus a sub n. So this is, remember, to find a sub n plus 1, I'm going to replace n with n plus 1. And so I've got 4 times n plus 1 over 2 times n plus 1 plus 1. And then a sub n is equal to that. And I'm going to go ahead and do a little distribution. So I get 4n plus 4 over 2n plus 3 minus 4n over 2n plus 1. Well, I've got two fractions. Maybe I should combine them into a single fraction. And so I'm going to find the least common denominator. That's going to be the product of those two. And so I get that, and now I need to do a little bit of multiplication. I think I get 8n squared plus, it looks like I get 8n plus 4n, so plus 12n plus 4 minus 8n squared plus 12n. That's pretty sweet. I'm going to include that in parentheses, you can. But notice I've got that 8n squareds cancel and the 12n's. It would help if I wrote the n there. The 12n's are going to cancel, and so it's going to leave me with 4 over 2n plus 3 times 2n plus 1. Since n is positive, that denominator is going to be positive, the numerator is positive, so that's definitely equal to 0. So an plus 1 is bigger than an for all n, and thus the sequence a sub n is increasing. Now, if it's increasing, to show that it's bounded, what I really mean is that it's bounded from above, that the terms don't grow any bigger than some number. And so let's take a look at this. So to show bounded, I need to find, so I'm going to show that it's bounded from above. I need to find a number that all these terms are definitely less than, or find a number that's definitely bigger than all these terms. Well, we've done a little bit of comparison in this course already. We're going to be doing much more in the near future. But remember that if I make a denominator smaller, that if I keep the numerators the same but I make the denominator smaller, I get a bigger fraction. So I can make this denominator smaller by subtracting 1 from it. But 4n over 2n is simply 2. And so a sub n is less than 2 for all n, so it's bounded above. And I hope that you'll be watching these videos and that you'll be asking questions about them when we get together.